Well, welcome everyone. It's an absolute pleasure to be talking to you today about experimental designs. It's something that I can get very excited about. So as an applied statistician, I've been very fortunate to work on many fascinating research projects, tackling a wide range of problems. And I've really come to appreciate how much difference a well thought out experimental design can make. So good design, it really sits at the heart of robust, reliable science. It underpins the quality of our data, the validity of our conclusions, and the strength of the knowledge that we gain. So before I get really into it, I thought it'd be useful just to reflect a little bit about what an experiment actually is. So at its core, an experiment involves a deliberate action, commonly called a treatment, that we apply to study its effect. And of course, in many cases, our experiment will actually involve more than one treatment. Now, these treatments are applied to experimental units. We then measure, observe, or classify the response of those experimental units to the treatments in some way. Now, experiments themselves are conducted to answer specific research questions. And importantly, very importantly, they provide a way to infer cause and effect. In other words, if we do this, then this happens. Now, a well-designed experiment controls all other variables so that we can isolate the effects of the treatments that we're interested in. So really our goal is to make sure that the treatments are the only systematic difference between our experimental units. There's a couple of core principles of experimental design. They are replication, randomization, and reducing nuisance variability. And this is also known as restriction, since it involves limiting or controlling sources of variation that aren't of interest. Now, these principles, you may have heard of them before, they're famously known as Fisher's 3 R's. And I just want to go over the next few slides, take a bit of a closer look at each one of them, starting with randomization. So randomization is the process of assigning the treatments to the experimental units so that each experimental unit has an equal chance of receiving any of our treatments. Our goal here really is to balance out any nuisance variation across those treatment groups, therefore making it more likely that any differences we observe in our experiment are due to those treatments rather than some kind of other annoying nuisance factor. So without randomization, confounding can occur, and this makes it really difficult for us to determine if those effects we see in our experiment are caused by the treatment or by something else entirely that we're not interested in and that we don't really know about. Another important aspect of randomization is that most statistical methods rely on the assumption of randomization. So therefore, it's also essential for our statistical inference to be valid. Now, really unfortunately, sometimes we think we've randomized treatments to experimental units, but our methodology is flawed. So here's a little example here. It's actually from a study that I recently reviewed. In this trial, 100 sheep were selected from a very large flock of more than 3,000 sheep at random. They were then allowed to mix in the yard and run through a race, very similar to the one shown in the picture on the slide. So the first 50 through that race, they were given the new drug, and the second 50 through the race were given the standard treatment. Now, the researchers believed this was randomization, but unfortunately it's not. So while the sheep themselves were randomly selected, they weren't randomly allocated to the treatment groups. Very importantly, the order in which those sheep ran through the race could easily introduce some bias due to some hidden confounding factor. If you think about it a bit, you could see that, perhaps that animals that went through first might be the faster, stronger, or more dominant sheep. And all of these, of course, will end up in the same treatment group. Now, we could argue, or the researchers could argue, that this wasn't the case. But because they haven't employed proper randomization, they do not have the same protection against bias due to these hidden confounding factors. So another R of experimental design is replication. Now, replication means repeating treatments on multiple independent experimental units. Now, our goal here is to capture the natural or inherent variation in the response. And this helps us tell whether those differences we observe in our data are due to treatment or they're just some kind of random chance event. Replication is also important because the more we have, the more precise and reliable our results will be. But alas, without true replication, for example, if we have pseudo-replication, which I'll talk a little bit more later, our statistical inference is invalid and we risk drawing the wrong conclusions about our research. Now, there are actually kind of three main types of replication. In a designed experiment, we're typically interested in true replication. That is, those independent measurements taken on independent experimental units that let us measure the natural variability in the population. However, sometimes our interest is in assessing the variability of, say, a measurement procedure or a piece of equipment, and in this case, technical replicates are of interest to us. Now, these are repeated measurements on the same sample that allows us to assess the variability of a piece of equipment or our measurement procedure. Now, the third type is pseudo-replication, and this is the bad type. Pseudo-replication occurs when data are treated as independent when they are not. Now, it can arise in two ways. Firstly, we can make mistakes in our experimental design. For example, we could use subsamples instead of true replicates. Secondly, it can arise from errors during the statistical analysis when the structure of our data is inappropriately accounted for. For instance, this could be in a clinical trial. If, say, we've got nesting of patients within clinics and the structure isn't accounted for in our analysis, then we have pseudo-replication. So here's a bit of a classic example of pseudo-replication, although in practice it can actually be a lot subtler and way more difficult to detect. So in this case, again, it's another animal trial. It was conducted to compare a new drug with the industry standard. So 50 animals from herd A were given the new drug and 50 animals from herd B were given the standard drug. Now, at first glance, it might appear that there are 50 replicates per treatment. Unfortunately, in reality, these are pseudo-replicates because the animals within each herd can't be assumed to be independent. And indeed, we would expect animals in the same herd to be more alike than animals within a different herd due to things like environmental factors, genetics, and herd management. And also, very importantly, it was the herd, not the individual animal, that the treatments were allocated to, and hopefully at random. So in this study, the true experimental unit is the herd, meaning there is only one replicate per treatment. those individual animals are just pseudo-replicates. Now, another practice that we have to be very, very careful of is bulking or combining samples. Now, this can be done for some good reasons. It can be done to reduce measurements cost or simply to provide enough material for analysis. However, sometimes it's also done simply because it's more convenient to do so. So let's consider, as an example, a plant trial with 20 true replicates per treatment, arranged in a nice designed experiment. However, at sampling, all 20 pots per treatment were combined into a single sample and sent to the lab, where then 10 samples were taken for nutrient analysis. So here's the problem. By bulking across replicates like this, the true replication has been lost. We can no longer estimate the variability between pots or treatments. Those 10 subsamples are not independent replicates. At best, they measure the analytical precision, assuming, of course, that bulk sample was well mixed. They do not capture biological variation. So if samples do need to be bulked, it must be done strategically and never across an entire set of replicates for a treatment. And also, very importantly, bulking needs to be considered during the design phase, not something that we do kind of ad hocly during the data collection phase. Okay, so this brings me to Fisher's final R, and that is reducing nuisance variability. Now, this means controlling or accounting for sources of variation that we're not interested in. Now, reducing nuisance variability is important because it improves precision, making it easier for us to detect true treatment effects. And it also ensures a fairer comparison between our treatments. And finally, it creates more efficient designs, meaning we get more information from fewer replicates, which is great. So one of the most important ways to reduce nuisance variation is blocking. Now, experimental units are rarely, or if ever, uniform. For example, in a field trial on a slope, plots at the bottom may be more fertile than those at the top. And in a medical trial, for example, patients may differ according to factors like weight, age, or health status. Now, we want to control for this natural variation in our experiment, and this is where blocking comes in. So blocking, very simple idea. It works by grouping experimental units into homogeneous groups so that the units within each block are as similar as possible. Now, once our blocks are formed, the treatments are then randomized to the experimental units within each block, once again helping us separate treatment effects from that natural background variation. By controlling nuisance variation, blocking, of course, reduces that unexplained variation, which improves precision, and it also helps guard against bias by balancing out differences between experimental units and thereby ensuring fairer comparisons between treatments. Now, in the world, of course, there are many potential sources of natural variation. But when thinking about experimental design, we can basically group them into two types. There are a priori differences. So these are differences that exist before the experiment begins and are inherent to the experimental units themselves. So they can include things like, the initial weight of our test subjects or the initial vigor of the experimental plants. However, there's also induced differences caused by the experimental conditions or procedures. So examples of these include things like the order in which the data is collected. Perhaps you might get better at data collection as you go through your experiment. You might get more tired, your equipment may get worn out or something. It also includes things like differences between assessors or equipment used. Even the most finely tuned and advanced pieces of tech vary between different individual pieces of equipment. So both these types of nuisance variation, both a priori differences and inherent differences, can and really should be controlled for using blocking. So arguably, one of the most kind of important types of experimental design is the randomized complete block design. In this design, experimental units are grouped into homogeneous blocks, and within each block, the treatments are randomly allocated to the experimental units so that each treatment occurs exactly once in every block. For example, in this wee illustration on the slides, we've got 3 treatments. The test animals' ducks have been grouped into blocks of size 3 based on similar weight. And then within each block, the 3 treatments have been randomly assigned to the 3 ducks. However, there are other types of designs with blocking that may be more appropriate depending on your situation. So for example, in field trials, row column designs, which block in both the row and column directions, are very important for controlling spatial variation across the field, such as fertility gradients or other nutrient gradients and things like that. And there are some rather beautiful types of row column designs, such as the doubly resolvable row column design. Now in this design, treatments are grouped into replicates across both the row and column directions, such that every treatment appears once in every row and column replicate. However, importantly, row replicates may span multiple adjacent rows, and column replicates may span multiple adjacent columns. And this provides some practical advantage while also helping to control for spatial variation across the field trial. So to illustrate this, here's a small example of a doubly resolvable row column design with just 6 treatments laid out in a 6-row by 4-column grid. Now in this layout, each column represents a full replicate. The row replicates, on the other hand, they tessellate across 2 adjacent rows in the layout. Now, I'd like to introduce you to my wonderful colleague, David Beard. And one of the many things David does is design and analyse wheat and barley trials here in New Zealand. Now, David introduced doubly resolvable row column designs into the program. And by analysing the resulting data properly, he was able to give the breeders a 20% reduction in standard errors. Now, to put that into perspective, this is equivalent to adding 2 more replicates to the 4 replicate trials they run. Now, given how expensive these trials are, and the fact that there are 30 trials per year run over a 15-year period, this is a fantastic example of how a well thought out blocking strategy, combined, of course, with the right analysis, can save an incredible amount of time and resources. So now I would like to share some experimental design stories from my work. The first one involves some research with a brilliant animal welfare scientist, Mel Hempstead. Now, Mel and I were planning an experiment to compare 4 different disbudding treatments on dairy kid goats. Of course, we could block the goats by factors like age, housing, animal care, carer, genetics, etc., to account for differences in management, environment, age, and other things. But we wondered whether we could do something even better. In addition, in particular in animal research, a key ethical principle is to use as few animals as possible without compromising the overall value and validity of the research. So, each kid goat has 2 horn butts. Therefore, we landed on a randomised incomplete block design. So in this design, 2 of the 4 disbudding treatments are randomly allocated, 1 to each horn bud on a kid goat. The design is also balanced so that each pair of treatments occurs an equal number of times within the same goat across the entire trial. So our proposed design not only helps control for this between goat variation, but it also reduces the total number of goats required, which is great. So we thought that was pretty good. But wait, we realised that there was a few more things that we needed to think about. So for example, what about potential differences between the left and the right horn buds? So there could be some type of systematic differences between the sides due to physiological factors, even things like operator handling or other subtle influences that we can't think of off the top of our heads. So to control for this, we balance the treatments across those left and right horn buds, and this resulted in 12 pairs of treatments. So a combination of the disbudding treatment and also the side of the head it was applied on. But then we got thinking, well, what about potential differences between the vets applying the treatments? So of course, things like skill, technique, or even equipment might differ between the vets that we were going to use in our study, which could introduce differences in the results. So to control for this, we assigned 4 replicates of 12 goats to the same vet. We also wanted to guard against potential effects due to like the actual treatment order, so also randomised the order within each vet's replicate. And similarly, we wanted to control for potential assessor effects during data collection. So for examples, assessors may have unconscious biases or differ in their measurement accuracy. So to help prevent assessor bias, we blinded our assessors to the treatments. And to control for assessor differences, like with the vets, we assigned the same assessor to a full replicate of goats. However, because vet and assessor effects were not really of interest, they were just a nuisance factor, for practical reasons, we decided to confound those vet and assessors. So that is, we paired the vets and assessors and randomly assigned these pairs to the replicates. Now that we were happy with our design, we sought animal ethics approval. Now here in New Zealand, this is a formal process that assesses whether the scientific value of the experiment outweighs any negative impacts on the animals involved. And it also critically evaluates the methodology, including the experimental design, which is very helpful for identifying potential flaws before the experiment begins. And I think it's such an important process for helping to ensure ethical and robust science. Anyway, during the animal ethics review, one of the things that came up was potential carryover effects. Basically, the concern was, could the treatment on one hornbud influence the response on the other? Now, fortunately, I guess for us, with 4 treatments, including one which was a sham treatment, our experimental design, together with the correct analysis, would enable us to estimate any carryover effects and adjust for them if necessary. And really interestingly and somewhat surprisingly, there actually did appear to be some carryover effects. That was a very important insight from the animal ethics review. But the story isn't quite over yet, because after identifying a promising disbudding treatment that was more humane than current practice, we needed to conduct a validation trial comparing it to the industry standard. Now, as in our first experiment, within goat treatment allocation seemed attractive. However, what about the potential carryover effects? Now, in this follow-up study, we only had 2 treatments, and had each goat received both, we wouldn't be able to separate the treatment effects from any potential carryover. So we went back to applying treatments at the goat level. This meant we lost that within animal precision gains we had in our early experiment, and we needed more animals for our work. But we avoided the problem of carryover, and indeed also the experiment would then better reflect what would happen in real world practice. You wouldn't have different treatments on different hornbuds. The same goat would receive the same one. So this carryover issue, which to be honest, we hadn't really considered until animal ethics flagged it, highlights the value of having your experimental design reviewed by others, including statisticians, of course, domain experts, and very importantly, the people who will actually be carrying out the experiment. Now, mistakes, they can be very costly, not just in money and time, but ethically as well. A poor design can waste resources, lead to an unnecessary use of animals or human subjects, and produce invalid conclusion. And it's far better to fix the design up front than to try and rescue the data later on. So now, let's consider generalizability. We've talked about how Fisher's third R, reducing nuisance variability, makes designs more efficient and inference more reliable. However, there's a trade-off. It can also limit how broadly we can generalize our results. Generalizability is all about whether your findings apply beyond the specific conditions and experimental units you've studied. Generalizability is affected by the representativeness of your experimental units to the population you want to make inference about, and how similar your experimental conditions are to the real world. So common pitfalls include using a very narrow range of experimental units, running experiments in highly artificial settings, or relying on a single batch of materials. Now, I just want to take a bit of a closer look at this last point because it's something that's often overlooked but can be dealt with during our experimental design if we think about it. So imagine an experiment comparing the growth of plants given 2 different nutrient products. The plants are randomly assigned to the 2 treatments, but only one batch of product is used. Now, this is problematic because batches of product can vary, and this variability isn't captured in the experiment. Consequently, the results will only apply to those specific batches, one which happens to be of product A and the other which happens to be of product B. So we can't tell whether our findings will hold for different batches. Now, to improve generalizability, a simple fix, of course, is to use multiple batches of product per nutrient treatment. That way, we capture batch-to-batch variability and get results that are more broadly applicable. Now, I want to share with you another story involving work I did with a medical cannabis company. Now, there was a new nutrient feed on the market, but before they considered switching to it, they wanted to see if it would actually increase the CBD potency of their 3 flagship cultivars. So the treatments here were 3 cultivars by 2 nutrient feeds. And when we discussed the design, it became very clear that it was far easier to randomize the position of the cultivars in the grow house than it was the nutrient feeds. So I proposed a split plot design. However, further practical constraints emerged. The nutrient feeds are supplied to the plants through dripper lines connected to a tank. And the photo you see was actually taken while we were setting up the experiment, and those little white pipes are the drippers that get inserted into the plant bags to deliver the nutrient feeds. Now, the first problem we had is that these drippers couldn't just be put anywhere. Their placement had to follow some type of practical systematic arrangement, as shown in the diagram on the slide, where the nutrient feeds alternated between the rows. The second problem we had was that there was only space for 2 tanks, 1 per nutrient feed. So if we'd gone ahead with the current design, we'd run into that single batch problem we talked about a few slides ago. So the company, they really needed to be confident that switching feeds would actually improve performance. So the inability to generalize results to other batches was a deal breaker. So our final design, therefore, was a bit of a compromise. We spread the replicates over time and did smaller monthly experiments. We had to keep the systematic feed layout, but we did randomize the order. So what nutrient was in the kind of the first row, we randomized. And we also used different batches each month to capture the variability in batches despite the tank constraints that we had. So hopefully, as the CBD example illustrates, the best design isn't just about statistical considerations. It's also about practical constraints. Now, often, if not always, we need to make smart trade-offs. So experiments are feasible, but still produce useful data. Okay, so some of those experiments I described were getting quite complex in terms of their layout, and complexity is indeed another important consideration we have to think about when designing an experiment. The more complex the design, the greater the chance something goes wrong. For example, at the design stage, there's more risk of things like accidental confounding. During implementation, setup errors might be more likely. At data collection, missing values may be more common. And during analysis, complex designs can make it harder to correctly specify the right model. So, a simpler design in practice might be better. We should always ask ourselves, can a simpler design answer our key research questions? We need to remember to focus on what really matters. So can we leave out less important treatments or factors, or accept a narrower range of generalizability? And we should try to avoid unnecessary complex structure. So ask ourselves, for example, do we really need those split plots, repeated measures, or crossover designs? And finally, we have to make sure that our design supports an analysis we can actually conduct and interpret. So again, we kind of see that good design may involve a trade-off, this time between complexity and simplicity. More complex designs can provide more information, high precision, greater generalizability, etc. But simpler designs also have advantages. They are often easier to implement, analyze, interpret. Of course, they can be a lot cheaper in practice to run. Now, planning for missing data is also very important when we're designing our experiment. Missing data, it's a right nuisance. Not only does it reduce statistical power, it also complicates our analysis, and it may even bias the results that could invalidate our conclusions. So during the design phase, considering both the likelihood and the type of missing data is really important. So if it's likely to be at random, things like equipment failure, you might want to consider including extra replicates, or you might have to take some actions like using filler plants and pot trolls to mitigate against space effects. But if missing data is related to treatment or response, it's much more problematical and it will likely bias our results. And in such cases, we may even need to rethink our entire experiment. So really, is an experimental design perfect? And that's okay. Overcoming limitations is important, but equally, it's important to recognise and acknowledge them. We should always be transparent about what our experiment can and can't tell us and frame our conclusions accordingly. For example, in much of the conservation research I've been involved in, the experiments are extremely expensive and logistically and ethically very, very challenging. So independent replication of treatments is sometimes not feasible. In such cases, we need to be very careful when drawing conclusions. Without replication, we can't definitively attribute observed differences to the treatments. Rather, we must interpret the results as descriptive and make this limitation really explicit when we are describing and sharing the results of our study. Now, good experimental design is not just about layout, it's also making sure that the data can actually answer our research questions. We need to ask ourselves, can the data be analysed in a way that addresses our research questions? Will we collect the right information in enough quantity and quality? Do we have the software, the expertise, and the time to analyse and interpret the results correctly? And finally, as mentioned before, we need to think about whether missing data could be an issue. So I've been faced with some challenging data sets during my time, and to be honest, it's quite surprising that I don't have white hair already. So in this example, the experiment had many, many treatments with an extremely complex structure. It was multi-site, with different different designs at different sites, and only a subset of treatments were included at each site. There were repeated measures, complicated by the fact that different treatments and sites were measured at different intervals. Responses were continuous. There were some that were categorical and there were some that were ordinal. And moreover, they were measured at different levels. So some were measured on individual fruit and some were measured on the entire site. And of course, we had a problem of missing data, some of which was potentially related to the treatment. Now, I do enjoy a good data analysis challenge, but there simply wasn't enough time or budget to deal with data this complex and this messy. And planning around the analysis during the design phase would have been great to address this problem. So in the previous slides, I've touched upon how good experimental design goes beyond just generating high quality relevant data. It also actually considers the entire research data pipeline. This includes data management and quality assurance, analysis and reporting, of course, data archiving and sharing, and matters related to ethics and data security. Now, I delve a little deeper into this topic in one of my blogs, Responsible Data Use in Scientific Research, which you can find on the VSNi website. And if you're interested also in the animal ethics side of things, I've also written a related piece on the role that statistics plays in minimising animal use in scientific research, and that's also available on the VSNi website. So finally, before we wrap up, I just wanted to share one last cautionary tale. Now, I'm currently working with some collaborators, writing a paper about pain management during castration. And if you're wondering why the little puppy's there, that's my dog just before he had to go in for his procedure. Now, an important question in our research was, how does a biomarker of pain respond to castration? Now, this biomarker happened to be a microRNA. But unfortunately, because the trial was run several years ago and because quite a few team members have come and gone, the lab methods describing how the biomarker data was quantified have been lost, and we haven't been able to find it. So as a result, the data's scientific value is now severely compromised, and it's probably not even publishable. And this is a really, really tough reminder that without proper meta-information, even data from well-designed experiments can lose their value. So in conclusion, I reckon good experimental design is replicated, randomized, and efficient. It maximizes the amount of information we get from the resources we have, whilst generating high quality, relevant, and generalizable data. However, it also needs to be practical and feasible. That is, it must fit within real-world constraints and avoid overly complex designs that are difficult to implement or prone to errors. A good design is also analysis orientated, ensuring the data we collect can actually be analysed to answer the research questions we care about. It should also be robust to missing values and consider the entire research data pipeline from design and data management through to analysis, reporting and archiving. And finally, very importantly, it must be ethical, respecting the welfare of the animals, plants and resources, and ensuring the science we produce is responsible and meaningful. I'd just like to thank you all very much for listening to that. I'd love to receive any questions or comments. Thank you.
Thanks, Vanessa. That was absolutely brilliant. I can see a lot of positive responses in the and all the questions and comments are coming flying in. Harry, I've seen that you've had your hand up a few times, so I'm going to allow you to talk if you wanted to ask your question or if you do have a comment. You're muted if you are asking something at the moment, Harry. Okay, whilst we're waiting, if Harry does have a question, got a question. Which experimental designs would be suitable if number of treatments are large, more than 200, and treatments cannot be replicated?
That's a very, very good question. So in plant breeding, p-replicate experimental designs are very common, in which you have some of your treatments replicated and most aren't. That would be one way of doing that. P stands for partial replication.
Fantastic. We also have a question from Alex Sullivan. Something that's been on my mind recently after meeting someone who would like to automate the trial process in order to better the data acquisition of agricultural trials is if you take the human out of the system, is it still the same system?
That's a lot to think about. Yeah, I don't know. Yeah, to be honest, I'm going to have to dwell on that a bit more deeply.
Okay, so we also have from Daniel Ariza, what tools do you use for effective random allocation of treatments to experimental units?
That's good. Well, so obviously I work for VSN, but my software tools of choice are Genstat, which has some really good randomization procedures, and also CycDesign. But if you don't have access to those tools, you can do things in Excel using random number generators as well to randomly allocate um, treatments to experimental units. And of course, there's tools in R.
Fantastic. From Faisal, we've got if we're conducting an experiment in a large field to compare plant performance, however, the field is highly heterogeneous with many environmental factors causing variation in plant performance. Even after using blocking, there are still areas in the field that remains non-homogeneous and could affect the results. How can we effectively control or account for this remaining heterogeneity to obtain more accurate and reliable comparisons?
Yeah, that's difficult. So the blocking, yeah, can help control some of that. If you've got a nice grid layout with a row column design with blocking superimposed over top, you can use some very nice spatial analysis to estimate and account for those spatial effects. And that's what my colleague David Beard does when he analyzes the grain and barley data set. So he actually takes advantage of this automatic spatial analysis procedures in Genstat, which will pick the best spatial model to deal with those spatial trends. Yeah. The other thing that can be done, although it can get expensive, is if there's particular things, variables that are affecting plant performance, to measure them in the field and incorporate those into your analysis as covariates.
Fantastic. From Kwame, we've got what are the best strategies for planning and handling missing data in augmented designs to obtain reliable results in plant breeding? I'd be very interested to hear about any experiences or lessons learned.
Yeah, that's a big question too. Again, it really depends on why the data is missing. If it's missing at random, so nothing to do with the treatments or the level of the response, it's a lot easier to deal with because it essentially won't bias our results. So we can just add in a few more replicates at the start to ensure we have sufficient statistical power. As I very quickly mentioned, there may be some actions that we have to take in practice to ensure that we don't induce some additional noise. For example, in pot trials, if the plants go missing around, then you have more space in your layout, so you might need to put filler plants in. However, if they are not missing at random, so they're missing because of the treatment or the type of cultivar they are, or due to the size of the response, this is a very difficult to deal with. The only real way of doing it is to come up with some way of modeling that the process that generates the missing data, and that's very, very hard. Yeah. So sorry, yeah, it's not much help, is it? It's
I
hard.
think it's as you say, it's a big question, and it's
Yeah,
probably tailored to each individual's
yeah.
design. From David Mayer, we've got if you don't know which unit factors are most important for blocking, what about just recording it all and using covariates?
Yeah, no, you can do that. If it's possible. Um, I guess if you are recording covariates, you are thinking of things that may be going to influence the response, and therefore you can still block on them.
And finally, at the moment, unless any more come in, we've got a question from Denisha. I think it's going to be another big, broad question. Which approach better provides optimization of experimental design in plant breeding trials, model-based designs or the traditional design-based models?
Oh, yeah. Well, that's hard. Yeah, I'd have to come back to you on that one. I need to think about that more. To be honest, my experience has been mostly in a traditional type of designs, and then with layering on top the appropriate analysis to deal with it. So yeah, yeah, we might have to pass that question on to someone like Emlyn.
Well, you've got a question in from Harry. I don't know if you want to say it out loud, Harry, or I'll read it out for you. Um, So he has asked how to convince researchers that randomization is important. It's hard when they are convinced that their experimental units are homogeneous that they think randomization is not necessary. Also, there is still a belief that randomized complete block design is better than they will get better because they will get better mean per treatment. The mean per treatment will not differ given the design in the balanced orthogonal, no missing data. Blocking in the RCBD is to increase precision by lowering standard errors.
So there's a lot to digest there. So that the first question about how to convince researchers that randomization is important is really hard, and I have worked with some researchers that it's been almost impossible to convince them that they need it. And the argument is that, yeah, everything's the same. Why would it be different? You can only really convince those people that are so steadfast in that belief when something goes horribly wrong for them. And by then, it's of course it's a little bit too late. So I don't have a good strategy always for doing that, aside from patiently explaining why it's a good thing. And actually it won't cost them anything really to do, and it provides a whole lot of extra protection. So why wouldn't you do it? Um, the second part about that was the randomized complete block design versus, was it the incomplete block design? So you're right, the randomized complete block design, it does have that really nice feature that if you don't have any missing data, then that the means that you get are the means, are just the raw means. So I
I,
don't get the second part.
yeah, so it said there's still a belief that the RCBD is better because they will get better mean per treatment. The mean per treatment will not differ given the design in the balanced orthogonal, no missing data. Blocking in the RCBD is to increase precision by lowering standard errors.
Yeah, yeah,
Yeah.
yeah. That's true. Yeah.
Yeah. And to the first point of Harry, I guess I wrote it down actually, the 20% reduction in standard errors and LSDs that David did in the doubly resolvable column design. I guess meaning they don't have to put as many replicates in. That's got to be a fairly convincing statistic.
Yeah.
Which leads me on to a comment I missed earlier actually from Pedro Souza, who is asking about that. Do you know if the work is available to be shared? What David did?
I do not know. I asked him for a quote and he gave me
Okay.
that lovely quote.
Yeah.
Um, it is commercial trials. I do know that they do publish some of their work, but David would be I'm more than happy to follow up with David to see if there's some information around that we can share.
Fantastic. We're getting towards the end, so I've got one more question here from Mohammed. I'm a plant breeder. We plant the wheat experiments in RCBD layout, but then we take the data and after analysis, I was remaining confused about how we remove the experimental error with formula and how formula know that the amount of contribution comes from experimental error.
Okay, so with a very, with your classic randomized complete block design, ANOVA would be your tool to analyze the data where your blocks are your blocking structure, and then it will provide you that information. It'll remove the blocking variability from those treatment means for you. If you've got slightly more complicated designs, say unbalanced, and you still have a blocking structure, linear mixed models with your blocks is either random or fixed. There's some debate about that. Will help you do that as well. Yeah.
Fantastic. Just on time. So yeah, that was brilliant. Thank you very much, Vanessa. That was really interesting. I'm sure lots of people are now thinking about the experiments they're designing and perhaps the ones that they've done already. That was really interesting. As I mentioned, if anyone has any ideas for future webinars, please feel free to put them in the comments, or you can email, I believe it's hello@vsni.co.uk. I'm sure Amy will put the email address in for you. And if there's anything, if there's any concerns you have about your experimental design and you'd like to talk about what you're doing, we do have a consultancy service. So please feel free to reach out. You can either reach out to me directly or through our info box, and we can see how we can best help you. But yeah, thank you everyone for attending. Thank you very much, Vanessa. That was really great. And hopefully we'll all see you at the next webinar.
Thank you very much, Owen, and thank you everyone.